All right, in this video lesson, what we're going to do is we're going to look at interpreting the data that we saw that was accumulated in the previous video. The last video was just showing you how they use ultraviolet or X-ray energy to knock electrons off, and then they interpret that information into these data with these various peaks. Okay. First thing we want to look at is what the peak or what the x and the y-axis represent. First, the y-axis represents the relative number of electrons. So each of these lines is going to represent a certain number of electrons. Now, in order to figure this out, you've got to be careful because they change the scale. I've seen a couple problems, and we'll look at some in class, where the scale changes, where every line does not always equal one electron. Now, in this one, it does. And the reason I know that is that this peak here is going to represent what's called what you know already, is the 1s orbital. Okay, we know that the s orbitals can hold 2 electrons. Henceforth, therefore, we're going to have 2 electrons in this peak. That's what this peak represents. So each line represents an electron. Okay, so I'm establishing that. Now, how did I know that this is the 1s? Well, we've got to look at the next part of the chart, which is the x-axis. Notice that we have a binding energy. The binding energy is the energy holding the electron in the nucleus. Remember, you got the nucleus with that positive charge and the electron with a negative charge. Well, there's a force holding that electron in place, right? It's keeping the electron in the atom. That's the binding energy. What we're going to do is we hit energy onto this electron to cause it to knock out of the atom. This is our binding energy because it's the energy that we have to use to overcome that force holding the electron in place. So, notice that the binding energy is backwards. Normally we start with a 0 here. They put the 0 down here at the bottom because they're trying to help you. They're trying to be nice. What they are trying to assume is that this here would be the nucleus. At this point here, we're going to say this is our nucleus at that corner of the axis. So therefore, these electrons here would be closer to the nucleus, while these electrons are going to be further away from the nucleus. Now, if electrons are further away from the nucleus, like if I have another electron that's way out here, you already know that this electron requires less energy than the electrons closer to this. Okay, so what we're going to see is that the electrons closest to the nucleus are always going to be put here first, and they are always going to require more energy. So this here is the energy required to remove the electron. Energy required. So it's the energy we have to put in to the system. So that would be endothermic from our perspective, because we're going to add energy to knock that electron out. So this is an endothermic process. It's very similar to ionization energy. It's very similar. Okay, we have another 2 set of peaks over here. Now these 2 peaks are clustered together because what we have here is our second energy level. So over here is our first energy level, and over here we have our second energy level. Now you remember that the second energy level is broken up into a 2s and a 2p. So therefore we have our 2s and our 2p orbitals. So what I'm doing here is I'm figuring out what these peaks represent, and I'm just deriving the electron configuration from this data. And that's the point of this, is that you have data to work with that you can then derive the configurations. If you think in the past, we never really did that. Now, I don't necessarily think this is that important, but it's on the AP test, and this is what we have to deal with. So I just want you guys to be able to understand how to interpret these graphs. All right, so I've got 2 electrons here based on the height of the peak, and this is a 1s because it requires the most energy. It is closest to the nucleus. Remember, this represents the nucleus of the atom. Okay, so electrons further out would now we get to our second energy level. All right, so we got our 2s, and again 2 electrons in the 2s. Okay, all right, now we need to figure out, notice this peak is a lot taller than the other 2 peaks. This is because there's more electrons in this area. So we can figure this out. We said that each line is an electron, so 1, 2, 3, 4, 5, 6. So what this structure is a 1s2, 2s2, 2p6 element. And if you look that up on the periodic table, you will get neon. The other thing you could do is add up the electrons. 6 plus 2 plus 2 gives you 10 electrons, and therefore neon is the one that has the 10 electrons, assuming that we have a neutral element, and I'm pretty sure that they're always going to keep these as neutral elements. Okay, so that's pretty much how you're going to interpret this. Just a couple things. Keep in mind that the energies are backwards. These are very difficult for students well, I'm assuming they're going to be difficult for students. I've never taught this before, so we'll find out in the next couple days. All right, so let's take a look at another one. Okay, let's look at another one. Let's take a look at this structure here. We're going to see, again, it's a very typical AP multiple choice question, supposedly, is what they're telling us. So if we're looking at this structure here, given the above spectrum, identify the element and its electron configuration. All right, so if we have the relative number of electrons, first thing we do is figure out, okay, remember our nucleus is here at the beginning, so therefore this is almost always, I can't imagine that it wouldn't be anything other than the first energy level, second energy level, and your third energy level, right? Because as the electrons get further and further away, you can kind of think of this as the energy levels. You maybe want to think about this as the first energy level, second energy level, third energy level. That might be a helpful way to look at this. And then remember that the second and the third energy levels are broken up into sublevels. Okay, so this would be my 1s. This is going to be my 2s, my 2p, and my 3s, and my 3p. Okay, so if I were to try to figure out what element this is, we can recognize that it ends in the third energy level. Okay, so we can right away eliminate boron from that, because boron ends in the second energy level. All right, so if we're going to get rid of boron, we still have aluminum, silicon, and sodium. Well, we're past the 3s. Sodium ends on the 3s, so we know that it can't be the sodium because there's no 3p that the sodium atom has in a neutral state. It then leaves us with aluminum and silicon. Well, if we look at this, we know that silicon, we figure out how many electrons there are in here. Okay, so remember we figured out 1, 2. Is this the same scale? Yes. How do I know that? Because I'm using my first energy level to figure that out. Since I can hold 2 electrons in here, each line represents an electron again. So therefore, what I have is a 3p1 energy level, okay, or sublevel technically, because it's a sublevel. So which one of these ends on the 3p1? Is it the silicon or is it the aluminum? Well, if you look up on the periodic table, you'll find that aluminum ends on a 3p1. Now, if I want to draw the configuration, I'm just going to do 1s2, right? Then I'm going to go 2s2, 2p6. Notice that this is 3 times taller than the first two peaks. 3s2, again, that matches those other two s's. And then I end on a 3p1, and that would be my configuration for this. Okay. One other thing I want to show you before I end here is take a look at this. The first energy level here, I kind of wrote over it, is 151 megajoules per mole. That's the unit that we use here, megajoules per mole. All right, so it's 151 megajoules. If we look at the other element that we had, okay, the nucleus here, I'm sorry, not nucleus, we look here, the energy is 84. All right, so the energy level for this one here, for the first energy level, is 84 versus the aluminum, which is 151. So why would aluminum's energy level, the first energy level, be so much higher than the one for, what do we have, neon? Okay, the reason for this has to do with the nucleus. The nucleus on the aluminum is a lot higher in charge. So what do we have? 6, 10, 13. So the protons here are 13 plus, right? That's 13 protons pulling on this first energy level. Therefore, the ionization energy here is going to be higher. Okay, it's important when we look at some other things later on. So just kind of wanted to bring that to your attention that they sometimes ask you questions about that. Okay, they might ask you questions about, take a look at this energy level being 0.58 versus the energy level for neon being 2.0. Why would the neon be so much higher? Well, because there's less shielding, right? We've got the electrons are in the outer shell of the second energy level, while when we look at the other one, this energy level here, the 3p, has the shielding of the second energy level and the first energy level. So again, everything that we looked at earlier can still be applicable. It's just that we're looking at it through different type of data. So hopefully that gets you started on PSE or PES or photoelectron spectroscopy, whatever you want to call it. And we'll look at some more examples in class. Thanks.